We now want to tackle some examples of HJM models. Here's just a quick summary of what we did in the previous video. We modeled the instantaneous forward rate using infinitely many stochastic differential equations as shown here, where W is a finite dimensional Brownian motion and alpha and sigma are adapted processes which are sufficiently regular to allow us to do the kind of operations that we perform on them. And we saw that if we model directly under the risk-neutral measure, then no arbitrage implies the following HJM drift conditions. In other words, the drift of the instantaneous forward rate is completely specified by the volatility structure that we impose on it. So let's now have a look at the simplest possible HJM model. So the simplest HJM model that one can think of is a model driven by only one source of noise, i.e. a single one-dimensional Brownian motion, and where the volatility structure sigma is constant, and the same constant for every maturity capital T. The risk-neutral HJM drift conditions then give us the following expression for alpha. And thus the risk-neutral forward rate dynamics must be given as follows. Recall here that f star 0t is the instantaneous forward rate that we observe in the market. If we integrate this stochastic differential equation, we obtain the following expression, as you can easily verify yourself. And if we then use the fact that the short rate is the instantaneous forward rate right now, in other words, it's equal to f little t, that means we must replace capital T here by little t, and we obtain the following expression for the short rate. Let's now have a look at the stochastic differential equation satisfied by the short rate. In other words, let's compute dRt. That means we must differentiate this with respect to t, but notice here that little t is in the place of the maturity variable. We must also differentiate this with respect to t, and over here we'll get a sigma times dWt term. And hence the short rate dynamics will be given as follows. Here, this is the derivative of the instantaneous forward rate at time 0 with respect to the capital T variable, replacing capital T by little t. Now, these dynamics ought to be familiar to you. In fact, these are just the dynamics of the whole Lie model, already fitted to the initial term structure. So note that whereas in the short rate framework we had to perform some tedious computations to get the whole Lie model to fit the initial term structure exactly, in the HJM framework this fit is automatically achieved. Next, let's have a look at the Hall-White-Vasicek model in the HJM framework. Recall that this model has the following dynamics, where B here is a deterministic function and A and sigma are constant. As such, it is an affine term structure model, i.e. bond prices are given as follows. And because the instantaneous forward rate is related to the zero coupon bond prices by this partial derivative, we obtain that the instantaneous forward rate is given as follows. Here the subscripts capital T refer to the partial derivative with respect to the maturity variable. In particular, the Brownian motion W occurs only in the short rate, capital A and capital B are deterministic functions, and hence if we take the differential of the instantaneous forward rate, we obtain the following. This sigma dWt comes from the differential of the RT over here, and we haven't bothered to compute the coefficients of the dt term because these will just be given by the HJM drift conditions. Now for the Hall-White model, and in fact also for the Vasicek model, we obtain the following expression for capital B. And hence if we take the derivative with respect to the maturity variable, we obtain the following. It therefore follows that the instantaneous forward rate dynamics are given as follows, and thus that the volatility structure for this particular model is given as follows. Now you can go and compute alpha using the HJM drift conditions and show that it reduces to the following expression. Let's now verify that the above model indeed leads to the Hull-White short rate model. Firstly, observe that the instantaneous forward rate satisfies the following integral equation, and thus that the instantaneous short rate, which is just the instantaneous forward rate right now, satisfies the following equation. Let's call the first two terms of this equation theta t. And let's compute the differential dRt of the short rate. In that case, dRt is going to be theta prime t dt. That's this term over here. And we also have to take the differential of the dw term. Now this term here has t in two places, namely here and here. If we take the differential with respect to this t here, we can differentiate underneath the integral sign and obtain the following. And that will be a dt term. And if we take the differential with respect to this t here, we simply obtain sigma e to the minus a t minus t dwt, in other words, sigma dwt. Now, if we look at this equation again, we see that this integral here is just equal to rt minus theta t, and that integral also occurs in dRt. So we can replace this integral here by r minus theta t, as we do here, and then rearrange things and define a function b as follows, to obtain that dRt is equal to bt minus art dt plus sigma dwt. This is the form of the Hull-White-Wassercheck model. And thus the above formulation of instantaneous forward rates indeed does give us the Hull-White model. Of course, we still have to compute bt, which is defined in terms of theta t, where theta t is given as follows. Since we know what alpha is, this is a little tedious, but not difficult. I'll just state the results. A little effort will show that theta t is given by this expression here, from which it follows that b is of the following form. Now this is the function b which fits the Hull-White-Wassercheck model to the initial term structure. Notice now that the HJM model, which is defined under the risk-neutral measure to have the volatility structure of the following form, will yield the Hull-White-Wassercheck short rate model. Now a few words about the Markovianity of the instantaneous forward rate process. Here's a simple example that shows that a typical HJM model need not be Markov, nor need it lead to a Markov short rate model. Suppose that we take the following volatility structure for the instantaneous forward rates. Using the HJM drift conditions, it is then straightforward to show that alpha is given as follows, and thus that the instantaneous short rate has the following dynamics. Using the equations that transform instantaneous forward rate dynamics to instantaneous short rate dynamics that we did earlier on. In particular, the instantaneous short rate will then be given by the following, and will actually be a finite variation process, as you can see. And so if we know capital X, which is the integral of Brownian motion, we will know RT and vice versa. But X is clearly not Markov, because knowing the value of X at time t will not give you the distribution of future values of X. In fact, you need to know the value of W at time t. And because X is not Markov, neither is RT. Now, lack of the Markov property implies that we don't get PDEs for pricing, and also that if we use trees, that these trees will be non-recombining and thus explode. In other words, it is computationally very expensive and you will typically have to resort to Monte Carlo methods. There is one case in which we do get the Markov property for the short rate, and this is when the volatility factors. In other words, the volatility as a function of little t and capital T factors as a function of little t and a function of capital T. This is, for example, the case in the Hull-White model. We'll leave this as an exercise. But there are also cases where we can ensure that a joint process given by the short rate and a process phi t, is jointly Markov. To quote a paper by Richkin and Sankara Subramanian in 1995, as a consequence, the burden of carrying full information on the term structure at each point is dramatically reduced. This is because you just need to keep track of RT and phi t at every time t and not the entire history up till time t. Now partial differential equations or recombining trees with two space variables, namely r and phi, are possible. Here is the result by Richkin and Sankara Subramanian. If we have a one-factor HJM model with the property that the volatility structure is differentiable in the maturity variable, then a necessary and sufficient condition for the price of an interest rate derivative to be determined by a two-state Markov process R phi is that sigma takes the following form, where eta here is an adapted stochastic process, which may of course be deterministic as well, and kappa is a deterministic function. In that case, phi, drt and d phi t satisfy the following equations, and bond prices take a form that looks a little like an affine term structure model. I will leave some of this as an exercise.